Welcome to lecture 14. In the previous lecture, we had seen the magnitudes of the different terms in the x momentum equation, and now we'll continue looking at the order of magnitudes of the different terms. I'm just showing the slide from the previous lecture. So this we wrote down the full momentum equation, and we wrote down the magnitudes in terms of the scale variables that we had introduced. Now in this lecture 14, so we'll continue with the same discussion. So here in the last lecture we introduced the pressure scale, which we had not introduced earlier, but we introduce it now. So again, looking at the magnitudes of the terms, so now we look at the magnitudes of the terms omega w and omega u. So omega w is smaller than omega u, given that w is less than u, as we had previously said, and that also means large scale geophysical flows are primarily two-dimensional. So this is true away from the equator, because near the equator the f star term, which is 2 omega cos theta, becomes large. So we'll just consider motions away from the equator at this point. So this term is smaller than the omega u term. Now, because rotation is of importance, so in all geophysical flows, and this is what we have emphasized repeatedly, that rotation and stratification are two important important contributing variables which control the dynamics of the geophysical flows. So the pressure gradient term, now which is the driving force, will scale as the Coriolis terms. Okay, so the driving force, the force behind the motion is the pressure gradient, and this will be balanced by the Coriolis terms, because we have assumed, and this is true for large scale geophysical flows, that the rotation is important. So now the pressure gradient term pressure gradient, which is the driving force, will scale as the Coriolis terms. So this means P by rho naught L will be of the same order of magnitude as omega u. So P equal to rho naught omega L u. So this is a reference value. So this is the reference value over which density can fluctuate. For typical geophysical flows, this dynamic pressure is actually smaller than the hydrostatic pressure. So it's important for us to know. So we are calling this pressure in the previous slide as the dynamic pressure. Because this is the fluctuation, this is a appropriate word for this. So this for typical geophysical flows, the dynamic pressure is smaller than the hydrostatic pressure. We call it dynamic pressure as the hydrostatic component has been subtracted from it, and the viscous terms are also small. So this I am saying in a more general sense. The viscous terms are important near the boundary layers, and we'll see how the importance of viscosity manifests itself as as a driving force in changing the dynamics of the ocean or the atmosphere near the boundaries. So we'll do that later, but as of for now, for large scale geophysical flows away from boundaries, the viscous terms have negligible impact. So viscous terms are also smaller. So this is one, these are two different things that will help us in determining the scales, simplifying the equations further. And remember that this is why we are doing this. We are trying to remove lots of terms so that we have a slightly simpler form of equations. So this nu u by L squared, nu u by h squared. So if I go back again to the previous slide, so these are the terms that I am trying to find the magnitudes of. So this is now smaller than omega u. So Coriolis, as you know, is important, and the Coriolis terms are important. Hence, the viscous terms have to be lesser than the order of magnitude of the Coriolis terms. So the same, we have used a lot of order of magnitude analysis to show that lots of terms are much smaller than some other terms that appear in the equations. So same arguments will hold for the y momentum equation also, because the same terms appear, similar terms appear with the same scale variables. Hence, I'll just say that, I'll just write down. So same scaling arguments apply for the y momentum equation. Now we look at the z momentum equation. So this is, we have completed the x and the y momentum equations, because y momentum equation also has variables which have the same scale variables. So now looking at the z momentum equation. This is not equations, this is equation, this is just one equation. So the z momentum equation, so just write down the equation. The total derivative of the vertical velocity minus f star u equal to minus 1 by rho naught del p del z minus rho g by rho naught plus nu del square w. We have already derived all these equations, the Boussinesq equations, and the density perturbation that is given by rho. Actually this is rho prime, but we have dropped the prime. This appears only when it is multiplied with gravity, because gravity is the strongest acceleration in this situation. So in all other places, density is replaced by just a reference density. So this is the Boussinesq approximation. So in component form, I'm just expanding the equation into all the components. We have done the same thing for the x momentum equation. So now, well, let's see how each of the terms scale. So trying to write with a different ink, let's say. So now the first term scales is w by t, because we have the partial derivative of the vertical velocity with respect to time. So u, the second term scales is u w by l. this third term also scales as uw by L. Please remember that x and y have the same scale variables L, and u and v have the same scale variables u. So this fourth term scales as w squared by h. The fifth term scales as omega times u. The pressure gradient term scales as p by rho naught h. The buoyancy term scales as g delta rho by rho naught. So the reason why you have written delta rho is because this rho is actually fluctuation. This is what we have repeatedly emphasized, that rho, anywhere that rho appears is a fluctuation rho. So the other three terms scales as nu viscosity w by L squared, nu w by L squared, and nu w by h squared, because the scale variable for z is h. So these are the order of magnitudes of these terms. So now the term w by t, so the term w by t so cannot exceed omega w, because of the constraint that we had put on the temporal scales of motion, which is of importance to us. So you can go back again a lecture or two, and then you can see why this should hold. So our temporal scales cannot be much different from the Earth's rotation rate. 1 over omega. So this is a constraint that we had already put on the flows of our system. Also, we previously justified that omega w is smaller than omega u, because w is smaller than u. So we've already justified this one, justified this assumption. So u by L is smaller than equal to omega, and w is smaller than equal to h by Lu, because this is the definition of um, w, and this w is much smaller than u. Now we can write uw by L, and I mean, this is again following from the terms that we had previously from the z momentum equation, is smaller than omega u because rotation is important. So other terms, so the rotation is the most dominating term here. So the first four terms can be neglected with respect to the fifth. That means these are the first four terms. So the first four terms are neglected with respect to the fifth term, which is the omega u term. And so now we'll see what is the ratio of the Coriolis to the pressure gradient term. So we first of all write down this conclusion. First four terms neglected with respect to fifth. The fifth is the Coriolis term. Now the ratio of the Coriolis to the pressure gradient So this is the ratio of the Coriolis to the pressure gradient. This scales as rho naught omega UH by rho naught omega LU, because pressure scales as this rho naught omega LU. We had already defined the pressure scale, and this is approximately equal to, this scale says H by L. So we have used the pressure scale that we had defined earlier. Okay, so hence the fifth term now, so the first four terms were neglected with respect to the fifth. Now the fifth term is small as compared to the pressure gradient term. In the vertical momentum equation. And why is that so? Because H by L is much less than 1. This is one of the defining characteristics of geophysical flows. The vertical dimensions are much smaller than the horizontal dimensions, and L can represent both X and Y. Please remember that H is always the vertical, L and X, L can be both X and Y. And we have given some examples of tornadoes and cyclones and oceanic currents where the vertical scales are much smaller. So because vertical scales are much smaller, this ratio is much smaller than 1. Okay, hence this conclusion, the fifth term is small as compared to the pressure gradient term, and the first four terms were much smaller with respect to the fifth term. Okay, so this becomes a simple problem, simply inequality, that the first four terms are less than the fifth term, and the fifth term is less than the sixth term. So all the four terms and the fifth terms are less than the sixth term. Okay, so this is just a simple inequality. So following the arguments, including that of the x momentum equation, so following previous arguments, and that from the x momentum equation, the viscous terms are also neglected in the z momentum equation. So we also neglect the viscous terms because we have seen that in the, we have given the same the arguments in the x momentum equation that these are much smaller than the Coriolis terms, and we hence we are neglecting these terms. Hence, so this both the terms that appears, both the types of terms, that is nu w by h squared and nu w by l squared, are less than equal to omega w, which is much less than omega u. So the last three terms are also negligible in the z momentum equation. So going back to the z momentum equation, so the last three terms are also negligible in this. Now the only balance that remains in the z momentum equation is interesting because it reduces its form to very simple one. This is equal to 0. This gives rise to 0 equal to minus 1 by rho naught del p del z minus g rho by rho naught. This is what the vertical momentum equation reduces to. Go back again to see how, the system, the full set of equation for the z momentum equation, and how when it looked slightly more complicated than what we have currently, and using the scaling arguments we have now reduced this equation to this form. So this is nothing but the hydrostatic balance which we have already encountered. So let's write it down also. This is the hydrostatic balance. Okay, so again, just to emphasize, this P is also this is a perturbation to the pressure, the background pressure, which is also in hydrostatic balance. Okay, so here we find that the pressure fluctuations and the density fluctuations are also in hydrostatic balance. So similar to how the background pressure and the background density were in balance. Okay, so the reason why we could simplify this whole this momentum equation, this I'm writing down again, the simplified from the momentum equation, the z momentum equation, 0 equal to minus 1 by rho naught p del z minus g rho by rho naught. So this is the simplified from the vertical momentum equation, and the reason why we could simplify this momentum equation so much is because of the fact that h is much smaller than L. So this is a characteristics of geophysical motions, and this led us to having a very simplified equation for the z momentum equation. So with the Boussinesq approximation, and the scale analysis that we have presented before, we get the final set of equation so we'll see why they are important. So we get the final set of equations, and these are let me write down in a different slide just to be sure that I put all the equations in one slide itself. So the x momentum equation, the y momentum equation, the z momentum equation, and the continuity equation. So this has a form del u del t plus u vector dot this u dot del u minus f v equal to minus 1 by rho naught del p del x plus nu del square u. The y momentum equation, del v del t plus u dot del u plus fu this is the y momentum equation. The z momentum equation is minus 1 by rho naught del p del z minus rho g by rho naught, and the continuity equation, del u del x plus del v del y plus del w del z is equal to 0. So we have the x momentum equation, the y momentum equation, the z momentum equation. Z momentum equation has been significantly simplified, and then we have the continuity equation. So we first use the Boussinesq approximation to simplify the full governing equation, And now we have done a scale analysis which is relevant to geophysical flows, and we have derived these simplified equations. So the continuity equation does not change its form. So the continuity equation remains the same. So there is one more equation which is left for us to understand. This is the energy equation, but we will in this lecture we'll just write these equations as so this is equation A, equation B, equation C, and equation D. So next we'll look at the energy equation, because that will close the whole set of equations, because right now we don't know how we have equation of state, but we don't know how the temperature equation or the salt equation would have been modified with these assumptions. We'll see that all these including all these equations will give us a set of equations which are cornerstone of geophysical fluid dynamics, and that is the reason we were doing this whole calculations of understanding the magnitudes of different terms and trying to simplify these terms so that these become numerically accessible to us. We can simulate these equations in a computer, and we can have some broad understanding of the geophysical flow processes that are happening in the atmosphere and the ocean.